Okay, so it's a joint talk with Daniel Nicutielli, joint work with him and many others that I'll mention later. I will discuss selective inference. Okay, I'll discuss two examples to bring out the issue of selective inference, the problems related to selective inference. Then I'll present a short review of the false discovery rate ideas that are in work and that have been in work. I'll talk about the false coverage rate, and then I'll talk about ways to do better than with the more well-known methods, the adaptive procedures, which are widely developed, combining studies and hierarchical studies in relation to these two, in general, and in relation to these two examples. The first example that I would like to discuss is work done here, Wellcome Trust Case Control Consortium, and it deals with the replication of genome-wide association signals that reveal risk loci for type 2 diabetes. This is a very large project that does association using SNPs, and this is the main table that appears in this science paper. Well, you can't read it, of course. I will just mention from this large one that it describes the results of the study in of the Wellcome Trust Consortium, then another study in the UK, then a study in France, and then a study in Finland, and then joins them together. So in order to see something, let me get into this one and look at the results. So you see for these 11 SNPs that are presented, information about the SNP, the region, and so on, 95% confidence interval, and then p-value for the association, 10 to the minus 8, 10 to the minus 5, 10 to the minus 6, 10 to the minus 4. Okay, so these are the results presented. What is the explanation behind the table? What are the chosen ones that are shown in the table? The first wave of validated SNPs sent for replication was selected from 30 SNPs which had in the WTCCC scan alone attained the most extreme p less than 10 to the minus 5 significance values. Okay, so this was the first wave. However, too few were discovered, and the second wave was needed, and they developed a heuristic approach to the prioritization of signals, p-values between 10 to the minus 2 and 10 to the minus 5 in genome-wide scan, corroborating evidence from association with type 2 diabetics from the companion studies, the Finnish US study and the DGI, then biological candidacy, multiple association with the same items, and that's about it. And as they report the results of this second part, this criteria would have led to the selection of SNPs within both these two regions for second wave replication, despite the modest evidence for association based on the original scan. Indeed, the enhanced signals observed at known susceptibility variance and reach p equals 0.0013 in the original study, p which is 10 to the minus 6 in the combined study. And the question that I have is, what can be said about these numbers? These numbers that reflect the uncertainty. You have to realize that there were 400,000 SNPs analyzed, so then 10 to the minus 5 maybe doesn't look that great. We are presented with results about a selected set, a very small set selected from the big ones. There is strong evidence for some of the associations there, there's no doubt about it, but we cannot quantify the uncertainty involved. What does a p-value of 10 to the minus 5 mean? What does a confidence interval at 95% confidence interval mean in this case? What does a combined p-value of 10 to the minus 6 means when you use the results of the last study that was combined to look for the signals in the first study. So the heart of the issue that I would like to discuss today is that we should be concerned about inference following selection. And I think this point was made very well yesterday by Jeff, that this is the heart of the issue, and what I would like to argue that FDR methodology can offer quantitative answers to all of these problems. My second example is from the study. I'm involved for years in the study of exploratory behavior in novel environment in mice. When you put a mouse into a novel environment, it starts to search around, look around. Sorry. Sorry. It starts to walk around, it stands, it snips, it moves, then it makes excursion into the novel environment, following movement and sort of wandering in place periods, and is near the walls, then he gets into the center at a very late time, stops there, and so on and so forth. Very rich behavior is being developed, and we can measure it, quantify it, and study it, and this is what is done in behavior genetics, in this part of behavior genetics. Okay. So once these measures are being done, a big study was conducted in 3 different laboratories, one in Israel, 2 in the States, and a long list of behavioral measures: distance traveled, rate of turn, length of excursion, maximum speed, and so on, were compared across strains and were found to be a large genotype difference in terms of for most of these behavioral measures. Now, interestingly, after one of this large experiment in the US, people at Maryland Psychiatric Research Institute took the tissue, the brain tissue, from the mice that were tested in their laboratories from 5 different regions about 8 to 10 days later, and examined the gene expression of the brain tissue of these same mice that participated in the experiment in this lab. So for each gene, we have 8 inbred strains of mice, 5 brain regions, and replications in each of these. And this raises a lot of extremely interesting questions, like what genes exhibit strain differences in expression levels over the entire brain, or what genes exhibit strain difference over specific brain regions, or for what genes and in what brain regions are expression levels correlated with specific behavioral traits. Now, notice that just this last research questions involve some 2.2 million association, 27,000 genes, 5 brain regions, 7 behavioral traits. So we're talking about a huge problem. Just the third one is a p-value of 10 to the minus 5 used before appropriate for this one. And if not, then we should go to a higher resolution. Will anything be discovered? So this is the main ideas, and what I want to present you now is the FDR approach to this selection problem. My work was done yesterday, so I just mentioned that the FDR is simply the expectation of the proportion of false discoveries among the discoveries. But I would like to mention why FDR in this form. If you inspect 100 features, then if 3 out of 60 come out significant, well, that's bearable. We know that in statistics, we are bound to make errors. We just want to keep them at a low level. But 3 out of 4, that's unbearable. So the point is that the FDR is adaptive in nature. Now notice that the same arguments holds when we expect 10,000 or 100,000. We look only at the selected set. So this error rate is scalable. Now, if nothing is real, controlling the FDR at level Q controls the probability of making even one error to be the same, which is linked to the FDR and not to the many other variations. But otherwise, the FDR is smaller than the probability of making one error, so there is room for improving detection power. I want to emphasize that in screening studies, it really captures the expected effort chasing red herrings divided by the total follow-up efforts. So if in fact you want to work in your lab with FDR of 0.25 because you don't care that much, you're welcome to do it. There's a big difference here between reporting maybe to the literature and making decisions for yourself. But for instance, in this study, the first wave was sent for a replication. I mean, you want to ensure that maybe not more than 50% of what you send to replication is error. There are other versions of the false discovery rate. Story emphasizes the conditional expectation given R is positive. And if you use a fixed rejection region, then you define this one to be if you use everything less than A, every p-value less than A is significant, and you get this definition. F1, as we learned yesterday, emphasizes the local false discovery rate, and I will not repeat it, but also recently he mentioned the expected false discovery rate. This is his notation, with the expected value of the false discovery divided by the expected number of the discoveries. It's a problem because there's no connection between what you discover in your experiment and the errors you're making in your experiment. So it's something easy to work with, but not that important. I would like to emphasize that in the so popular mixture model used in microanalysis, all three are the same. Okay, FDR, positive FDR, and this expected or average FDR, they're all the same in this asymptotic model. Now, the important point I would like to make that they cannot be controlled when nothing is real, which is not in the mixture model, but they give more perspective on FDR, and they give the Bayesian interpretation and the empirical Bayes interpretation, again, that was discussed yesterday. I would like to reiterate my comment from yesterday. I think there is useful information in the local FDR. It can serve the experimenter very well when he wants to actually choose individual genes to further work on them. But when the estimation methods ignore the initial analysis selection, that is the selection of genes, the signals that were selected for analysis, when it ignores that, you're bound for trouble. And so far, nobody tried to address this selection to analysis, which is so common in all of these technologies, where there is a lot of problems. The problems tend to concentrate exactly where there is no signal. For the benefit of the more biologically oriented, those with curly headings, if you don't understand it, forget it. The next slide or the next slide, we won't make use of that. So just keep in mind this. Another issue that, another error rate that being offered recently by Genovese and Wasserman, Lehmann and Romano, van der Laan and others, they emphasize actually the tail probability of the false discovery proportion. That is not its expectation, but the probability that it will be above 0.05. This is a very attractive criterion. However, if we want to control this probability at some low level, less or equal to beta, then it is a stricter criteria than controlling the expectation at Q. So we are back into the direction where we don't want to be too much in the FWE or controlling the probability of having of making at least one error, and we'll have to see more as we gain experience with the practicalities of this. Now, the other suggestions were made where you allow yourself a fixed number of errors. Say the probability of making at least 3 errors is less or equal to something. And similarly in the FDR, there has been such recommendation. Again, the problem is calibration across different studies. One chooses 2, one chooses 1. What will you publish? So if it's for your own work, they may be useful for your own analysis. For publication, less so. Okay, I think most of you are familiar and were presented yesterday with the linear step-up procedure that controls the false discovery rate. Let me just give a quick example. In the case of controlling the FDR in the brain and behavior example, two-way analysis, the research question is, are the difference in expression level between brains? So I do an ANOVA and take the p-values of strain effects. And here's the plot of the p-values against strain effects. And we know that for the main of them, it should be approximately uniform along a straight line. And then there are those, the promising one. Now, what we do is the linear step up, pass a line between Q over M, going all the way to Q, check for the first intersection here. Let me explode it. Okay, so you see the place where it cuts it. Now, I usually stopped here, but in the last month, I encountered 2 papers, one of them in JRSSB, that made a mistake here. Notice that the linear step-up says that if the plot wasn't like that, but was instead like that, then you would still stop at the same cutting place, because you start from the largest p-values until you hit the first crossing. You don't stop, and then you don't look any longer at what happens here. This is not the other way around. They're going this way, which is more conservative and so on. I'll make use of this property, so beware of that. Adjusted p-values is just another way to reflect the rejection by FDR or the comparisons to FDR values. If here are the raw p-values, we can create adjusted p-values by taking the sorted p-value multiplied by m divided by j, and then looking at all those bigger than it. And these adjusted p-values have the property that if all null hypotheses are true, they have uniform distribution. So in that sense, they can also be used for testing, and we'll make use of that.
Can I ask a question? So you've got a two-way analysis of variance, and you're looking for strain effects. These are genes you're looking
across
for
the brain, yeah.
Gene by gene. But what if it's a two-way analysis of variance with main effects for your second factor as well as the strain, and presumably some interactions.
That's, in fact, I erased the interaction because of time limitations, so you introduced it. Yeah, in fact, we were interested in the two of them. Gene effects is not, I mean, there's not much of an interest, but certainly interaction.
My question is, how many p-values do you have in there?
Okay, so
with all of the main effects jointly, or just one of the main effects?
that's the essence. I mean, each one of this is one research question, looking at the p-values net. A different research question is the one association with brain and behavior, and I'll combine them all at the end. Okay, this is a crucial question. I mean, we have a family, one research question with a family of hypotheses, another research question with a family of hypotheses.
But right now, when you correct your p-values,
now I looked only at this research question. I asked what brain, I mean, in what genes are the difference in expression across the brain, across the strain. So, okay. What about the control by linear step-up procedure, the BH procedure? Suppose M naught of the M hypothesis are true. If the test statistics are independent or positive dependent, the FDR is controlled by this method at M naught over M times Q, which is less or equal to Q. Now we have another beautiful mathematical theory which brought us a lot of trouble. Because in general, what you can show is that the FDR is less or equal to M naught over M times Q times 1 plus a half plus a third and so on, which is Q times log M approximately. Doesn't grow by much, but it is bigger than Q. And this statement, in fact, that this is this one and it can achieve, somehow gave the impression that the linear step-up procedure breaks down in some sense under dependency. And this is totally wrong. There is no need for inflating factor in microanalysis, association studies, and so on, where the test statistics, or every place where the test statistics approximately Gaussian, and probably in many more situations. Let me give you some understanding about the pathology of the example that gives this increased FDR. This is the extreme joint distribution for m equal 2. The p-values are uniformly distributed here, uniformly here, uniformly here, uniformly here, but at each one of these with alpha over 2. So overall you have here 3 over 2, or q over 2, q. Now, think about this kind of strange joint behavior. In m dimension, this is again these kinds of points and strips. Anything that has some regularity to it won't show this example. Now, in fact, if you take this kind of problem, here is one realization from the extreme, such an extreme distribution for m equal 2000. I mean, any other method will clearly see that this is the null hypothesis, this is the alternative, it will have 2 spikes, it will estimate, and will fall into exactly the same trap, but with no hold of what is going on. So there is no, whenever these things go into trouble, they go into trouble together. We are on the same boat. Luckily, the boat is not in rough water, and in fact, the FDR controlling procedure works well even when the correlation is 1 between all genes. I mean, it's exact even in that case. In a recent study, Anat Reiner took the issue of X normally distributed with mu and sigma. The worst FDR control was when the rho ij was 1. That was done via simulation. But once this was discovered that the worst case is 1, then we could investigate and see. First of all, when all null hypotheses are true, the FDR is exactly Q. When m naught was less than mu, the worst case was some mu's at 0, some mu's away from 0, correlation 1 here, correlation 1 here, and negative correlation between the blocks. Okay, even this thing was analyzed analytically, and what you can get is the FDR is controlled at Q times m naught over m times 1 plus m naught over m times 1 minus m naught over m. So actually, using the BH for this two-sided approximately normal test guarantees that FDR will be less or equal to Q. There is no need for inflation factor when using the BH in microanalysis and association studies, whether it's normal, chi-squared, and so on. There should be no problem there. Now, adaptive procedures might run into the trouble because you see here that m naught over m, and this can get as high as 1.25. So if you want to use an adaptive procedure and it's worth it, inflate a little bit your Q. Last point, which is crucial for the people working here, for example, in SNPs data. Suppose we have block dependencies of 1. I mean, really, the SNPs are in the same haplotype, and so any association will be exactly the same. So the procedure says take the p-value and sort them. If you take only 1 from each block, and compare this one to m naught over m times q, and so on, pk plus 1 to k plus 1 m times q, until you find that pk is less than k over m, and so you reject all of this, right? Now suppose you have a block, that is, this pk is repeated j times, so all of these p-values are the same. What will be the linear step-up procedure look like? Well, you start with m plus j divided by m plus jq. You start from the same place. You continue to go all the way, and you compare pk plus j to k plus j over m plus j times q. But this one is bigger than k over m times q, and pk, which is the same as pk plus j, was less than that. So obviously, you will reject from here. So if you rejected 1 in the SNP, you will reject the entire block. You will not lose from the dependency in this kind of structure. So in fact, a bit more discoveries in the combined study, and it will be by the right amount. Okay. Now I want to get into a less known area, and this is the issue of the false coverage rate, or offering FDR methodology for confidence intervals. In the diabetes study, there were 10 confidence intervals after selection from 400,000, and each one of them was done at the 95% level. Okay? The p-values started from 10 to the minus 5, but the confidence interval started at 95, remained as usual. This is a common theme. A subset of parameters is selected, interest lies in the selected parameters, but when it comes to confidence interval, nothing is done. In fact, ignoring confidence interval is more common, as we see, or ignoring the multiplicity and selection effect is more common in confidence interval. Why is that? Well, there are various reasons given. First, Bayesian reasoning, you have to look only at the marginal inference. Frequentist confidence interval is more informative than just hypothesis testing, so we're already doing better science. That's something, a quotation from an article. Since we're doing confidence interval, we won't correct. But there is a more serious claim voiced, and this is that the confidence interval gives the right coverage on the average. That is, for 95 confidence interval, the expected number of the intervals covering their parameter divided by the parameters is bigger than 0.95. Thus, at most 0.05 out of the interval constructed will not cover the respective parameters, just like a single confidence interval. So why should we care here? And I would like to first give a simple example of why we should worry about it, okay? We are selecting things that we are selecting parameters that their estimators are away from zero, and constructing confidence interval for them. So for each of these, this is a confidence interval, this is the estimator, this is zero, and the dotted red is the true mu's, which are the same for all of them. Now, if we look at this confidence interval, we see that this one doesn't cover its parameter, and this one doesn't cover its parameter. So in fact, 2 out of the 11 do not cover if we have no selection. But suppose we now select only the confidence interval that do not cover zero. Okay, makes sense, that's what we do. So once we do that, we have only 3 confidence intervals that do not cover zero, and in fact, on the average, 2 out of 3 do not cover the respective parameter. So the issue is that even if we are interested in the average coverage selected is not, over the selected is not the same as the average coverage in general. So we have to realize that we have 2 different concerns when we talk about multiplicity concern. One, it's the effect of simultaneity. Sometimes we want that the probability that all intervals will cover their parameters at the same time will be, bigger than 0.95. So the goal of simultaneous confidence intervals, such as Bonferroni inflating and so on, is to assure that the probability that all will cover jointly will be at the desired level. But in the effect of the selection, we simply worry about the fact that the subset of parameter is selected for highlighting and the average coverage deteriorates below 0.95. We introduced the false coverage statement rate, where a falsely rejected hypothesis is identified with false coverage statement, a false confidence interval that doesn't cover the interval, and false discovery rate, we talk about FDR of confidence intervals, and we defined similarly for any selective procedure, if RCI is the number of confidence intervals constructed, that is the size of the selected set, V out of this confidence interval do not cover their parameter, we define the proportion of the non-covering if a confidence interval was constructed and 0 otherwise, and the false coverage statement is simply the expected value of this proportion. And we claim that it's a good thing to control the false coverage rate over the selected ones. Do we have a procedure that allows that? Well, the procedure is very much related to the linear step-up procedure that controls the FDR. If selection is made by testing whether mu I equals 0 using the linear step-up procedure, we know that the number that we reject is we compare HPI with I over Q times M and take the largest one, okay? This is the, so R is in fact the size of the selected set. So now what we add to it is that for each selected mu I, construct a marginal 1 minus R times Q over M level confidence interval. So we inflated it by the amount that the p-value has to pass there. So this is direct relationship, okay? R is the size of the selected, R times Q over M. So you see that the inflation is large if the selection is small, and the inflation is small. In fact, if all are selected, there's no inflation. We are working with 1 minus Q. And for independent estimator, this confidence interval enjoy false coverage rate less than equal to Q. And in fact, even if the selection is general, not related to mu equal to 0, and is not based on these testimators, I like to call them, that when you test and estimate, okay, the result still holds if we use R to be the size of the selected group. There are some small computational things that might change, not always, but basically it's the size of the selected set that determines the level of the interval. I'll finish this part with a small example. Sample 100,000 mu i's, 45,000 of them have exponential 1 distribution with plus or minus. 5,000 have exponential 10, again with plus or minus signs given. And then data is generated, normal mu I 1. And for each mu I, you construct a confidence interval, a regular confidence interval. And the unadjusted confidence interval, of course, cover 95.089 of the 10,000 parameters, which is fine. That's what they are supposed to do. Notice that we don't have any mu I equals 0. All null hypotheses are false. I could reject all of them and have FDR 0, okay? Because there's no mu I which equals to 0. Still, when we look at the selective inference, okay, and look at all those xi which are bigger than plus or minus 2, I mean bigger than in absolute value than 2, then only 2,320 out of the about 6,000 of the selected intervals are being covered. That is, when we are here, the proportion not being covered is deteriorates. We can introduce the false coverage rate controlling procedures, which increases the confidence interval just by the right amount to get false coverage rate of 0.052. So we have here a viable, simple, very simple alternative that allows us to inflate the confidence interval. And in fact, if you use FDR to select your p-values, the confidence interval will not cover 0 because it uses the same p-value on both sides. So it is consistent in this case. Now we claim that this selection problem appears in the Bayesian framework as well. Even though the actual distribution of the parameters is unaffected by selection, and therefore inference that corresponds to the distribution of the parameters in the sense that you're using a Bayesian model with empirical Bayes priors in the mixture model where you estimate the proportion pi naught there of the null hypothesis. It provides a valid inference even for the selected parameters. But Bayesian inference that incorporates other non-informative priors or informative priors that are not based on the data has to be adjusted for selection. And the conditional likelihood is the correct likelihood for the selected parameters. And then a standard Bayesian inference based on the conditional likelihood, it has been developed, and Yekutieli paper is in the archive, can be reached. And in fact, from the few experiments we made with it, it even controls the frequentist false coverage rate issue. Okay, that much about technology. Part of it known, part of it new, but how well do we do with the example at hand? What happened if the if the Wellcome Trust Consortium has used the simple BH approach using the p-values in the table. Well, here are the 10 p-values. They are sorted. We calculate for them the adjusted one. So here is the list of the 400,000 times pi is divided by I. We look at, for each one, for the maximum over the list below it. It remains the same. These are ones, where the p-value is bigger than 1. And what we have is the short list of 2 findings out of the others. So we could have better results if I had the entire set of p-values, because in fact, the fact that there are correlated p-values can help here and reflect correctly. Still, I mean, that's not much. Can we do better than that? Well, better than that is usually associated, usually goes in 2 directions. First, if the prospective proportion of discoveries among the search one is large, if we have many things to discover, then the direction is the adaptive procedure, and that direction has been well developed. If the prospective proportion of discoveries among the search one is small, that is, we're searching for diamonds in the hay, very few findings among the huge ones, then I'll present 2 new ones. One is combining studies, and the other one is hierarchical testing. But first, about adaptive procedures. Recall that we had an m naught over m, or p naught, or pi naught in yesterday's talk. This is a factor by which the FDR procedure is conservative. And if m naught is known, then using the linear step up with q times m over m naught, inflating q by m over m naught controls the FDR at the level exactly the right level. So this is an FDR oracle. The adaptive procedures try to estimate this thing and to plug it inside, multiply, inflate q by that amount. And interestingly, it all stems from work in '86 by Schroeder and Schottfold that say that if you have many p-values, you can look at the figure of them, and those that correspond to true null hypothesis should somehow show linear behavior, and from the linear part you can estimate m naught. And this idea has been followed. We used it back in 1990 for FWE enhancement of Bonferroni and so on. And we have some procedure, and there are stories, and there are bootstrap search and parametric modeling, as we saw yesterday, on the uniform distribution, parametric modeling on the z-scores and mixture models and EM algorithm and the ratio and so on and so forth. Okay, there is really a very active area of research. In spite of that, there are 3 procedures that actually assure FDR control. That's all among them. All the others are somewhat more optimistic, and they become optimistic as m naught over m gets closer to 1. First option is the Story, Taylor, and Zygmunt suggestion, which is a modification to the original story. Use some predetermined alpha, or a, say a equals a half. Take the number of p-values above half, plus 1, and divide by 1 minus half. And then use the BH with q times m over m naught, but add the condition that only reject p-values less than this a. And this was shown to control the FDR under independence. In fact, of all the 3 suggestions that I'll bring it most powerful under independence, but it is also very sensitive to dependency. In spite of what is written, if you take dependencies that you encounter, like comparison with the same control, it runs into troubles. One warning, the estimator can get bigger than m. There is nothing here, and in fact you need the expectation of this to be correct, so you can estimate it. Number of true null hypotheses can be greater than the number of hypotheses that you actually test. It can be even negative. It should not be tempered with, or it loses its FDR controlling properties. Second suggestion by you could hear Lee Krieger and myself, use the linear step up once, but with a bit stronger control, q over 1 plus q. And reject whatever you reject. If you don't reject, stop. If you rejected something, then estimate m naught at m minus r, or m minus the number you rejected. Again, inflate it a little bit and use it again. You can think about the theoretical version. If you do it once and it controls the FDR, try to do it twice and 3 times and so on. It seems reasonable. It works in simulation. We don't have a proven result for that. The third one is the multiple stage step-down procedure. You start with I equal 1 and go all the way, continue to bigger p-values, and you compare each pi with I times q divided, instead of m, by m plus 1 minus I times 1 minus q. Where does this come from? Well, again, at this stage you reject I, so you would use m minus I as your estimator for m naught. Well, but some of the i's are false discoveries. How much? About q of them are false discoveries. So take m plus 1 minus I times 1 minus q. And there's a proof that this one controls the FDR. This is work with Yulia Gavrilov and Sanat Sarkar. What's interesting is that this procedure has excellent performance as a model selection procedure. You can introduce this as a penalty and get penalized residual sum of squares, or you can even simply do it with your regular software. Just do forward selected repeatedly with p to enter modified. Start with the p to enter conservative. Then if you enter some things into the model, check what should be the next p to enter. Work like that continuously and you will enrich the model. This can be done with any standard software, SAS, PMDP, and so on. And in about 1 or 2 iterations, it reaches the same place as the penalized thing would reach you. And it has very good performance. Now, are these adaptive procedures helpful when you're talking about the problem of searching for diamonds in the hay? In very large studies, only a handful of the true findings will be true. And if m naught over m is too close to 1, adaptive procedures that really control the FDR run into trouble. If you look at the 2 stage that I mentioned, if m naught is bigger than m minus m times q, then you start from less attractive position, and it may help you, but you may lose. If you use the Story-Taylor-Zygmunt one, if m naught is bigger than m minus the square root of m, estimate m naught might be bigger than m quite often, and in fact, if under this condition, with probability 1/6, you will do that, and then you will have to lose over the regular one. So we have to look elsewhere for increase of power. This will not come from making adaptive procedure better and better. So the one idea is to combine studies. And this is in fact the idea that was behind my first example, the diabetic example. You say, okay, one study is too low in power, and they analyze the power. 2, 3, and so on, then you might have more. So there were actually 3. One of them was split, so I'll talk later in my data about 4 different diabetic studies combined, dealing with the same scientific question. So how can we combine the evidence in face of selection? Well, what I would like to suggest is the partial conjunction analysis approach. What does it mean? A full conjunction hypothesis is to say that SNP S is associated with the disease in all 3 studies. Okay, in all of them. Now, this is the strongest scientific statement that we can make, right? That it appears that it's in all of them, and probably too strong. I mean, it will be quite impossible to prove that in all studies it is happening, and we'll relax it. But I would like to warn that just choosing the SNPs that came out significant in 1, significant in 2, and the other so on, intersecting them won't help you. I mean, they don't control at all any error rate. In fact, FDR can be as high as 1. So how can we relax the full conjunction hypothesis? Here, for the full null hypothesis, we have to reject the null hypothesis that at least in 1 study, the null hypothesis is true. if we use the partial conjunction H1, 2, 3, we say that the SNP is associated with disease in at least 2 studies. Well, then we have to reject the null hypothesis that at least in 2 studies the null hypothesis is true. And if we go one step further, we can ask that the SNP is associated with disease in at least 1 study. Well, this is the weakest scientific statement that we can make. Here we have to reject the null hypothesis that at least in 3, i.e. in all of them, the null hypothesis is true. Okay? So this is a sequence of scientific statements that are weaker and weaker as we go along. How do we do this kind of thing? Well, we take the results in study 1 and take SNP S. We take the results in study 2, the same SNP. And then we take all of the p-values, all the 3 p-values in the 3 studies. And let's put them aside, sort them, and we'll get the sorted p-values for SNP S. Then, for testing H33, we use the largest of the p-values as our test statistics. For testing H23, we combined the largest and the second largest p-value. And so on, if we have more studies. For testing H1, we combined all 3 p-values. And how do we combine it? Oh, before that, after we get a p-value for each SNP, we continue like before with FDR controlling procedure. How do we combine it? For testing, say, H23, we combine P2S and P3, the largest and the second largest, and we can use either Fisher test on these 2, if they are independent studies, as they are here. We can use the BH adjusted p-value that I mentioned in the beginning. It is a valid p-value. It's the minimum of 2 P2S and P3S. And this is when they are positively dependent or approximately normal. Or even we can use the Bonferroni, which in this case will be P 2 times the smallest of the 2. And the details are in a paper in biometrics. What will it give in this case? In this case, I conducted the analysis with the data given, and what you have that if you look at least 1 study, then there is quite reasonable evidence in all of them that this is after the selection with FDR. If you go to at least 2 studies, that is, you ask, is it replicated, is the result replicated at least in 1 more study, then the situation changes. And you have here 1 and 1 and 0.9 and 0.3, and only 6 of them show that. If you ask for, is it replicated in at least 3 studies, then we have only this single one well-known thing. So, the 1 point, it can help you gain power. It can also put you in perspective where you are in terms of scientific statement. I'm very happy with saying that at least in 2 studies we've shown evidence that this SNP. I'm not so happy with at least 1, and there were quite a few more with at least 2 than there were with the 2 single ones that were with just showing in the 1 study that you had. I looked at at least 1, at least 2, at least 3. Is it legitimate? I'm doing each one and FDR separately. The previous method allows looking at least 1, at least 2 jointly, and so on, and we can discover more steps. The point that I would like to summarize before passing to the last issue is we can offer protected search or quantify the uncertainty in face of selection even when we combine studies, and this is the essence of selective inference I'm talking about. Okay, so now to the last strategy, searching for diamonds in the hay. The idea is to use initial screening to limit the pool of the tested hypotheses to those that are potentially fruitful, and then test the remaining hypotheses. And if you do it correctly, it is a very effective strategy. There are various ways which I will not discuss. For instance, screening by weighing using prior information by putting weights on the hypothesis. That is, you use initial screen, you put weights on the hypothesis, and you use weighted FDR controlling procedure There is our approach, there is the approach by Genovese and Wasserman. Both fit different purposes, but they serve the same idea. They also allowed to introduce prior weights in the form of Bayesian priors. The second idea is to screen by testing selected hypotheses on the different data sets. So do the double FDR. Do an FDR selection at the level of 0.2 at the first screening. Just then take only the hypothesis that's past this screen and do again an FDR selection at level 0.25. In fact, the combined study has FDR of the multiplication of the thing. So you work here at 0.2, here at 0.25, and the FDR of the procedure is 0.025. The reason? The fact that you have controlled the FDR in the first phase says that the proportion of null hypothesis in the search ones is already bounded. So you can make use of that. Porsche et al., Bauer and so on, they actually did first a screening at the 0.1 level, just uncorrected. And then only those passing using an FDR of 0.05. And they showed that in many designs it's much more effective research strategy than just running everything, using all your data and all of your sources on everything at the same time. So just this idea, basic scientifically correct idea of screening and continuing with the promising one is very fruitful. And I will demonstrate screening by testing different yet related hypotheses. And I'm back to my second example. So remember the research question for what genes, what brain regions are the strain expression levels correlated with specific brain behaviors. So this is an association. It was studied using Spearman, but the problem is, can we use this, what we know about the problem, to give us more power? Well, the fact is that we know that there are strain differences that affect the behavior measurements. So let's go to the brain regions. Let's go to a single brain region and see if there are strain differences between the expression level. If there is no difference between the expression levels, there is no potential association. If there is, it's not the same. You can still have no association at all, but there is promise to detect something. So screen for genes and regions in the brain for differences in expression levels. Then test for association traits only in the genes and regions that pass the screening. And for that thing, we have two FDR controlling approach, selected subset testing and hierarchical testing. I will demonstrate them graphically. So you have the strain differences that you test at the level 1, and only few of them, each one of these is a hypothesis about strain. Now, everything that passes the strain, then you take at the level 2, you test for association. The first one takes all of the children that pass the screening and together test using FDR control on the entire thing. The second one, the hierarchical testing, tests each children of the same parents together, these 17 hypotheses with FDR controlling procedure. So the advantage of this, we use a much lower level. Do we control the FDR of that? I will just describe the results of the hierarchical testing. So we used, I'll explain in a minute why, the 0.025 level for the first step. We then tested subfamily separately at the 0.025. The number of traits by genes by region discoveries were 123. And the point is that even though we did it many families separated, each one with FDR at 0.05, there is a theorem in a work by Yukutieli that says that the joint error has to be about 0.073. It has to be bounded by this figure. And in fact, the simulation showed that this one is approximately 1 in many cases, so we can simply half the p-value we are working with. These are the results of the analysis. Here we have the 17 behavioral measurements. Here we have the different regions in the brain and specific genes. And we view the correlation, either a positive correlation or negative correlation. We see only the significant ones, whether positive or negative. The other ones are blackened out. The point is that if they did not pass the FDR thresholding, I'm not sure even about the direction of the correlation, whether it's positive or negative, so I'd rather not show it at all. Now, how does this method perform when I look at this kind of studies? So here's a small simulation study where we studied the power of the BH procedure, adaptive BH, the subset selection that I mentioned before, and Article 3 that I emphasized later. When P naught is 0.82, could be 0.8, but fine, okay. Then what we have is the power is 0.76, adaptive gains something, subset selection does worse, hierarchical 3 does worse. When we get closer to 1 at 0.99, we're 45, 45, 44, 49. When you are really searching for the few, 0.998, BH original is 0.929, adaptive doesn't help much more, subset selection already shows more, and the hierarchical 3 is much more effective. In fact, it hardly loses here across that. So the idea is that even though millions of tests may be conducted and many more tests considered and research questions posed after viewing the data, research questions come, appetite comes with the eating and so on, we can ensure reproducible results by working in this hierarchical setting. I will just explain the idea of it, not get into the theory. The whole idea of this hierarchical setting is that you arrange the hypothesis in some families. And this is, of course, related to the content of your research. You try to have things that you think will either all be null or there will be quite a few. I mean, very non-homogeneous things. And then you test together all hypotheses at the same level. Those that pass, those that you reject, you continue down to the second level. You test this one separately and see whether you reject. You test this one separately and see what you reject. And you continue with what it is. Here you reject the two together and you reject here. Here you don't continue at all because you didn't reject here. So the idea is to go on with the tree, and interestingly, in this full tree, there is a theoretical results that if the test statistics are independent, the FTR upper bound is 2 times a delta times Q, where delta is 1.44 in theory, but again, much smaller in practice. So the point is that your FDR level is at most inflated by 2 if you are combining a large study like that, but there's no limitation on the number of levels in this case, in this statement. So you can continue this way, and in some sense, it helps you get this one. Okay, I will skip this one and just finish with the general approach for complex statistical analysis. The analysis is divided into separate research questions. That each one of them has many questions. The research question can be added at a later date. An FDA is structured for each complex research question. And there's no problem to continue this research question. And you care about FDR control for each research question separately. Now, and here I'm speculating, our current understanding is if the number of research question is less than the number of discoveries, total discoveries overall, then FDR is controlled in the entire study altogether. In fact, there is a theoretical argument to show that if we are studying things that are approximately the same, then the FDR control is exactly the same always. That's a joint work with, in asymptotic setting with Donohoe and Johnston and Abramovich. Okay, I'll finish up just by reviewing that FDR methodology offers an appropriate and rich enough platform to address testing, confidence interval, combining studies, selection, screening, hierarchical studies, using prior information. All of this we are now in the situation to incorporate within the FDR framework. There are many methods, and I'm sure some of you were overwhelmed by the many things I threw out, but there will be more. I'm sure about that. Differences are smaller than they seem, but as I pointed, sometimes the differences are crucial and may harm you if you don't pay attention. We're searching for a few discoveries among many, combining studies and screening approaches, and in particular hierarchical screening, are the promising direction, and I believe they are fruitful direction as well. Thank you.
So perhaps we have time for one or two questions before we go for coffee. Questions? Or caffeine? Okay, Mike?
Maybe just a comment for the biologists on a small detail in your talk. Can you flip back to the point where you introduced the confidence intervals? You had a nice picture of 10 confidence intervals. Let's comment not so much on the question of selection, which I think Yoav and I sort of have a very similar view on, although we see it through different lenses. As it's just a very basic point for the biologists, since that's what the statisticians are supposed to be doing here at this meeting, is that, of course, in your previous slide, your first bullet was that some people say you don't need to worry about the multiplicities here if you take a Bayesian point of view, because all you care about is the marginal distribution. And in a Bayesian world, these would be marginal posterior intervals of some kind for a Bayesian analysis. Well, of course, in a nutshell, that's correct. But of course, that presupposes that a sensible Bayesian analysis is being done. And in any sensible Bayesian analysis, whether you're dealing with multiple studies or multiple comparisons within one study, a hierarchical analysis, which is what a sensible analysis would be, always leads to, in this sort of framework, shrinkage of these intervals to zero. So the intervals, the marginal intervals, will tend to sit around zero more than they do in the unrelated analyses. And they could get longer or shorter depending on how the model is structured. But that's the fundamental essence of why one can say that in a Bayesian analysis you don't need to worry about the multiplicities. It's self-correcting. It's not the selection.
No, you're right in the sense that in Bayesian analysis, the confidence interval will not look the same, and in fact will not necessarily be centered in the way that I presented it.
But fundamentally, predicated from this perspective, that there's lots
fundamentally,
of they will be shrunk to sit around zero much more than the marginal independent analyses do, which is why, and that aphorism is apt, but it presupposes that you're doing an analysis of all of the data collectively and not just analyzing each of them individually. That's the whole point. The multiplicities are self-corrected when you analyze things collectively.
The point is that when you analyze it, whether you analyze it based on law, if you look at the entire set and then select subset for highlighting, for
not talking about selection.
then that's a select.
Basic meta-analysis perspective.
Well, but that's the well, I'm showing you. That's fine, but
I'm convinced this is going to happen over coffee. Just
that's.
Let me make a comment.
No, that's.
That was just an invitation for the biologists. As far as I could tell from the talk so far, most of the biologists are Bayesian anyway. So.
No, let me clear out. Okay, just 1 minute. It is a fundamental. I mean, this last statement is a very touchy issue because, really, in the traditional framework of Bayesian framework. Somehow selection, if it's done correctly and appropriately, the selection, every selection should appear into the model. And in that sense, there is total agreement between the two of us. The issue of selection now creeps in very unnatural ways, as we've seen also yesterday, and that's the point I was trying to make.
Okay. Coffee.